Welcome to Complexity Made Simple. My name is Paul Allen and this is video 8 of the Catapult case study. So if you haven't watched them, go back, watch the other 7. You can see how we got to this point. And in this video, what we're going to be doing, we are in the analyze phase, but we are in the analyze phase 2. In other words, this is the second time that we visited the analyze phase in this project. And this makes the point that define, measure, analyze, improve and control, it isn't linear. Yes, you do start at define. Yes, you do finish at control. But do you bounce around in between? You absolutely do. So let's take a look at my presentation as I've created it so far, so we can remember how we got to this point. So if we look at this, the define phase, of course, was we had too much variability. So your define phase, you only have 2 problems. Have I got too much variability, or am I missing the target? Do I need to improve my aim? In this problem, we had too much variability. So because we had too much variability, the tool that we fetch out of the box is process flow, cause and effect. So of course we've done that, and what we've done is we've reduced the variability right down, and now what we've got is a really consistent process. So now that was our first round of define, measure, analyze and improve. The analysis was the variables and their state of control. So because it was about variability, the control was all about reducing the variability of all the inputs to the process. And that's what we did. That was analyze phase 1, and analyze phase 1 was physics. Now that we have consistency, analyze phase 2 is mathematics. And now what we're doing, we did this test where we did the pullback angle on the catapult. We created a model. So it was simple linear regression. We created a model. We confirmed the model. We hit the target, so the model's working perfectly well. But at the end of video 7, I said, is that really going to be a system that we're going to use? Are we going to use linear regression? Well, of course, if I go to the catapult on the computer here, and you can use this to practice along with me, I've got an extra variable now, which is the cup rotation. So in total, I've now got 6 variables on the catapult. Now, do you really think I could do 6 linear models and hit a target with 6 independent linear models? No. So that doesn't work. The other thing, of course, was when I did the test, I tested in multiple positions, I think about 8 or 10, and I created the model. I didn't really need to do that, did I? What's the minimum I could have got away with? Well, I could have got away with 2 points for a linear model. Which 2 points would you take? You'd probably go low and high, and then you can join those dots together. But in order to get confidence in that model, I'd have to take a sample size. I'd have to do multiple shots up here, multiple shots down here. Now, usually 30 to 50 is what we're aiming for. So let's assume I go 20 there and 20 there, 40 data points. If I've got 6 variables, 6 times, I'd have to do a sample of 40 for each test. So, simple linear regression. Number 1, it's not going to work because our systems are more complicated than that. Number 2, it would be data hungry. So it's data hungry, and it doesn't give you the knowledge that you want anyway, because we want process knowledge. So what we're going to show you is how to do tests on multiple variables at the same time. And that makes the situation data efficient because we're only going to use one sample size to do this. So it's one sample that tests all 6 variables at the same time. So we're going to take a look at that. I'm going to introduce to you now design of experiments. And what this technique does is it gives you process knowledge fast. So we're going to step outside the Catapult for a second, look at an alternative system that looks more like maybe a molding machine or a CNC machining center, some kind of machine that you'd have in front of you. And then we'll step back and we'll take a look at our 6 variables on the Catapult and just tell you what test we're going to do in the next video. So let's introduce design of experiments. So we're trying to develop process knowledge. Now, why can't I just fiddle with my process and get process knowledge? Surely any experiment is okay. Whereas what I'm going to teach you to do is to use specific experiments. Well, I just want you to think about the challenge that might be in front of you. And it's like this. You have a system, and it doesn't have to be a mechanical system, by the way. It could be a marketing system or a recruitment system. But typically what I major in is physics. I'm in manufacturing, physics, chemistry, biology, maybe, you know, real processes where real transformation takes place. So you have, let's call it a transformation process. Okay, you are trying to get process knowledge for that transformation process. Why can't I just do some experiments and I'll find out and everything will be lovely jubbly? Why can't I just do that? Well, this is the challenge that's in front of you. Imagine that you have 6 input parameters. Now, of course, often these are dials. All right, so we can adjust the settings on our process. So let's say they are time. So we'll pick something which is very physics in nature. Time, temperature, pressure, speed, angle, material. Okay, so there are your 6 parameters, and we say that the window that you're interested in operating in is, let's have a look. Time, the window is 10 seconds to 20 seconds. Temperature is 400 to 410 degrees. Pressure is 3 bar to 13 bar. Speed is 40 to 50. Angle is 30 to 40. And material, let's say there are 10 different materials. Okay, so you've only got 6 inputs. How difficult can it be to get process knowledge and optimize this system? By the way, on the output side, let's have a look. Let's say we've got dimension A, and we've got, let's say, surface finish. So 2 things that we're trying to optimize, and of course what we're trying to do is find the sweet spot. Can I hit dimension A and get the surface finish that I'm looking for? And there could be another one which is strength, all sorts of different parameters, and you're trying to find the sweet spot in those customer related measurements typically. How difficult can it be? Well, look at this. Time has 10 choices, temperature 10, pressure's got 10 choices, speed's got 10 choices, angle has 10 choices, and material has 10 choices. So how complicated is this system? Well, it's like this, isn't it? If I just moved these two settings around, 10 times 10, there's 100 combinations just in those two. Well, if I keep going, of course, times 10 times 10 times 10, etc., what do I get? I get 10 to the power 6. There are 1 million combinations. 1 million choices. And you need to find the best one. How do you do that? How do you do that? Now, because I use design of experiments, I can tell you that if I attempted this particular problem, I would have between, let's have a think, I would use between 20 and 20 to 28 experiments to answer that problem. I already know that. I already know that because I'm going to use a designed experiment. By the way, then I'll understand the million combinations. I'll understand where the best settings are. How about that? That's design of experiments. It is the fastest way. It is the fastest way to find out. It is the fastest way to find out the most process knowledge in the quickest possible time. It really is. It is like when I do this in a real class, I say to my students, look, this is like standing on the top of Everest. You are standing on the top of Everest, the absolute peak of process knowledge. But if you step just a meter in any direction, where do you end up? Down in the weeds. That's the difference between design of experiments and any other experimental technique you will learn. It is the fastest way to find out the most information about a system. It's the fastest way to find out. Okay, now you saw how complicated that little example was. Now I made it relatively simple by saying there was only 10 choices on each of those 6 variables, but it makes the point. Obviously, real world, you could have billions and billions of combinations in the real world, maybe trillions even. So, what we're going to do now, let's take a look at the catapult, the electronic catapult, and see how many variables we got. Well, what we've got, look, is we've got the rotation of the cup. Now that's got 90 degrees. We could go from 0 to 90. So 90 choices in that case. We've got the cup position. The cup position. And that goes, I think it goes from 200 to 300. So 100 choices. We've got the elastic position. And again, I think there's 100 choices on this. The elastic position goes from 100 to 200. And that gives us 100 different positions that we could test it. We've got the pin position, which is at the front there. So the pin position, and the pin position goes from 100 to 200. So there's 100 choices in there. We've got the stop, so that white peg just on the arm there, the stop position. Now this interferes with the arm, so this is an angle setting, this interferes with the arm. So we're going to restrict the stop position to just 100 degrees to 120 degrees. So that gives us just 20 choices for the stop. And then finally, of course, we'll have the pullback angle. So the angle is going to have to go a little bit more than that because we've got to create some movement. So we'll go 130 and it goes back all the way to 185 degrees. So what's that? That's 55 choices. Okay, so there's the problem on the electronic catapult. 6 variables. We're going to test them in 2 places, 2 levels. But if I tried to understand all the combinations, because don't forget, what I want is the best settings. So the best settings are going to be somewhere inside this design space. That's what those combinations are. It's your design space. Let's multiply them up. If you multiply these together to create the number of combinations in your system, what are we going to get? We are going to get 99 billion choices. Now, what do you think? Do you think you could carry this knowledge around in your head? You can come up with the cheapest, fastest, best settings to please your customers every time, for every product, for every system, for every tool in your company, for every different item that you make, for every machine that you make. It's ridiculous. You need a tool, and we're going to use design of experiments to do this, because design of experiments, as we've just said, is the fastest way to find out the most for your system. So when we come back in video 9, I'm going to show you how to start experimenting on this design space. Now, there are 2 techniques you're going to use, 2 techniques in DOE. There is a technique called screening. Screening is all about understanding the vital few variables. In other words, of these 6, which variables make the system dance around the most? Which one can we really use to bully the process and make it land on any target that we ask? Okay, so screening is going to reduce those 6 variables down so that we can then go modeling. And modeling allows you to create a maths model to hit targets. A maths model to hit targets. And that's what we're going to do. So when we come back in video 8, sorry. Now it is video 9. What we're going to do is we're going to show you how to screen using something called the Taguchi L12, and that's going to screen those 6 variables down. We are just going to use 12 tests to do that, and that will be coming up in video 9. Video 10 will be a full factorial, modeling DOE, and video 11 will be a 3-level DOE, because we're going to look for curvature. Maybe these models aren't linear. Maybe it's more complicated than that. So that's 9, 10 and 11 coming up. We're going to be showing you in video 9 the Taguchi L12. Look forward to seeing you next week.